Hello, and welcome back to physics. We discussed in my last little mini lecture, anyway, the idea of coordinate systems in 1D and displacements, and vectors versus scalar quantities. And where we're going next is defining how quickly this displacement occurs. And that is done via, as you probably expect, a velocity, not a speed. And we'll talk just a little bit about that, either in this context or another, okay? But a velocity. A velocity has both a magnitude and a direction, just like a displacement. But it is different, right? A displacement appears in the definition of velocity, right there, okay? And so since our delta t is generally positive, right, time marches on, well then our velocity, our average velocity here in this definition, and our displacement are always going to be in the same direction, positive or negative, whether that's up or down or left or right or whatever, okay? But the velocity gives us more information, right? It tells us the rate at which we're changing our position, right? And that's an important bit of information if we're trying to describe the motion of an object, all right? So we've got velocity. This little bar indicates that it's average, right? And with these deltas, as before, it's final minus initial, and initial time tends to be taken as just 0, though if you're looking at sort of a sequence of events, you can imagine labeling it otherwise. Now, there's a few things we should keep in mind about velocity, and to start fleshing it out, we should look at a position versus time graph that I've got sketched out over here with some axes on it, right? So position in meters, usually good practice to indicate your units on the axis of a graph, and time in seconds. Those are the standard units of position, and displacement, so meters, length, and time for seconds, okay? And that makes the units of velocity, if we look at that just briefly, that makes the units of that meters per second, or meters over seconds. Now, if we imagine an object moving from the origin of our coordinate system to a point that's maybe 5 meters out from our coordinate system. So if you're just looking at an axis like we had on the last mini lecture, just looking at position changing, but not worrying so much about time, you might look at like that, and that's 0, 1, 2, 3, 4, 5. And so that's the equivalent move that we're looking at here, okay? But the idea of this x versus t graph is to show how that position is changing with time, and so we need this second axis to represent that. Now, the slope of this line represents the average velocity between 0 seconds, right here at the origin, and 3 seconds, all right? And why is that? Well, I mean, just look at the definition of velocity, right? If we just multiply both sides by delta t, we get something that looks like this. And if we remember back to our Math 100, I guess, would be sort of, you learned it earlier in that, okay? But this, if we remember on our graph that the delta x quantities, so the final and initial x's, those are on the y-axis, and our times are on the x-axis. And that means that the v here is our slope, m, in the usual sort of y equals mx b, or mx plus b, okay, if there's some sort of offset. We're starting at the origin here, so we don't need that, okay? But that's telling us that the velocity of an object is the slope on a position versus time graph. We'll see that that's generally true. It's true for any point, but it's certainly true here when we have a final position and an initial position, and we can use this to calculate that. Now, if we actually calculate that out, right, we've gone 5 meters in 3 seconds. So 5 minus 0, because we started at the origin for our numerator, and 3 minus 0 in the denominator, for a grand total of 5/3 meters per second during this period of time. And we can add to that, and I will, if we have this object moving, now it's gone out 5 meters and it comes back 3 meters, so that it's 2 meters from the origin. And it does that second move in about 1.5 seconds, so going from 3 seconds to 4.5 seconds on this x-axis. Okay, well, the slope of that line again represents the average velocity between 3 seconds and 4.5 seconds. But if we were to instead just look at the first point and the third point in this sequence, well, then that gives us a completely different average velocity, because even though this object, whatever it is, has gone back and forth a little bit, so there's a lot of detail that we're missing. If we just look at the final initial, like we see here in the definition of average velocity, well, then that would tell us that the slope of this line, which is much, much smaller than these other two, well, much, much smaller at least than the other two, that the average velocity for this whole move, right, over 4.5 seconds is, what would that be? So let's see. Delta x is, final is 2 meters, initial is 0 meters, final time is 4.5, initial time is 0, and so we end up with this sort of awkward fraction of meters per second, okay, for that third interpretation here, okay? So one, this is just giving you a little practice of seeing how these quantities slot into this definition up here, okay? But also it's pointing out that when you're talking about average velocities, unless your velocity isn't changing very much or your position is changing very consistently in a certain direction rather than sort of going out and then coming back a little ways like we have here, well, then you're missing some information. And sometimes that's fine. We don't really need to know about all the in-betweens. But other times we are interested in that, and it's just important to know that distinction. Okay. Now, if we wanted to know exactly what the velocity was at any instant, and we knew a function that could tell us what the position of the object was as a function of time, well, then this definition, this one down here, is the one we would use, okay? So if we have a function x as a function of t, okay, and we take the time derivative of that function, then we will get the velocity of the object as a function of time, okay? So you could do a simple one, right? If you imagine an object that had a function describing its position that was, I don't know, related to t squared, right? Let's just say 2t squared for just to give us a function. Well, you take the derivative of that, right? You pull down a pen, okay, and that will give you v versus t, okay? The other thing to remember about a derivative is its geometric interpretation, okay? A derivative is the slope of this, right, which is the derivative of this, okay, is the slope, right, of that function. And so our earlier discussion of how, well, when we took the final and initial positions, we get our times, we get the slope there being the average velocity. Well, it turns out to be generally true at any point for some more complicated curve like we have over here, okay? At any point there, the slope of that line is going to be equal to the velocity of the object because we're looking at position versus time, okay? Now this question, what can we tell about the velocity of an object at each point? Well, I mean, technically we could sort of go through here. If we had a function, like a mathematical equation for x versus as a function of t, then we could just take its derivative mechanically and figure out what the v as a function of t graph must look like. We don't have that, so we just want to look at it abstractly. So at 1, right, we have a positive slope, okay, relatively significant in size. We'll see how it compares as we go through here, but a positive velocity. At 2, near as makes no difference. We're looking at a horizontal line that's tangent there, so the slope is 0, and so the velocity of this object, whatever it is 0. We have the same situation at 3 after going through a period of time where there's a negative velocity. So it's like something is moving in one direction, stops momentarily, turns around, comes back a little ways, turns around again at point 3, and accelerates very quickly and gets up to a very high positive velocity here at 4, and then comes to a stop briefly at 5, and then kicks it into reverse and has a negative velocity all the way down from 5 through 6 and down to 7, where it again momentarily comes to a halt before going off to do whatever it's going to do. Okay? So this is a pretty abstract model. You can imagine something sort of putting it into first, going fast, putting on the brake, smoothly putting it into reverse. I mean, we're losing some detail here with the smooth curve, but you get the idea. Going out and coming back, and going out and coming back, and so on and so forth. All right? The important thing, velocity is the derivative of the x. The x is a function of time. And that is generally true at every point, and true when you're talking about average velocities as well. And that's a nice thing. So where we're going next is a discussion of acceleration, but I'll see you another time for that. Goodbye.